Hi everybody. In this presentation, I'll be explaining how the resting membrane potential is established, um, the properties of the cell membrane that account for it, and how it affects its magnitude. And then I'll discuss action potential, its phases, and how it's compared to graded potentials. And then finally, I'll explain capacitance, the length constant, and the role of myelin. As a starting point, let's look at the resting membrane potential, or RMP. In most neurons, this is negative 70 millivolts. So let's show that. We've got a cell here, and it is negative on the inside, positive on the outside. Negative 70, to be specific, on the inside. It develops as negative because it's selectively permeable. Potassium ions can leak through potassium channels. While sodium doesn't move in as easily. Um, so potassium. Potassium leaving. That being said, there is the sodium pump, sodium potassium pump. So sodium comes in and potassium comes out. Plus here. It will pump in 3 sodiums, pump out 2. Most of the sodium stays outside though. But this is where we get things like action potentials when sodium comes inside. But the resting potential, getting back to that, the resting membrane potential, it depends on ion gradients, so how much sodium we have and how much potassium we have and other ions. The membrane permeability, how quickly it is to come in and out of a membrane, and pump activity, this pump here, how much it's going to move ions. The Nernst equation, it helps us calibrate the equilibrium potential for a single ion based on the gradient, which, simplified, Nernst equation is 61. Write it down here. So I'm going to do this. 61 log, and then in over out. Oh wait, other end. Out over in. The driving force is the difference between the membrane potential and an ion's equilibrium potential. And this tells us which way the ion is going to move. Either inside the cell, so we could have sodium coming inside the cell, or coming outside the cell. Okay, that's the membrane potential. Closely related to that is action potential. This is a rapid all or nothing electrical signal. So I'll show you with a graph. What would happen here is we would have the resting membrane potential, and then it's going to go through depolarization, which means that it's going to rise. Say this is negative 70, 0, we'll say this is 30. It's going to rise. This is when voltage gated sodium channels open and sodium starts to rush in. This is depolarization. This is when it starts to rise, and then at a certain point, once it hits threshold, it pops up. And that's action potential. This is really when the sodium rushes in and stuff. Then we have what's called repolarization, meaning it's going, or I guess this is more hyperpolarization. It's going back towards the resting membrane potential. This is when the sodium channels are inactive and the potassium channels are open and potassium starts to leave. So that starts to come down. However, the potassium channels stay open just a little bit too long, so they go below the resting membrane potential, and then it drops below the negative 70. Then we have something called the absolute refractory period, where no action potential can fire, and the sodium channels are inactivated, and the reflective refractory period, where some sodium channels recover, but extra stimulus is needed because the cell is still hyperpolarized. But this is when it comes back up and goes back to resting membrane potential. Okay. There are different things. There's something different called a graded potential. A graded potential are very small and local, and they vary in size, and also fade over distance. So on this graph, we extend it. Oh, that's real bad. It's more just like a smaller bump, and it gets smaller as it moves away. Where our action potentials are all or nothing, and they're always the same size, and they travel long distances without fading. So this would be more like psh, psh, psh. That's an action potential. Okay. Now I'm going to talk about capacitance. Capacitance is how much change the membrane can store. How much change the membrane can store. A bigger capacitance means slower voltage changes. And the length constant measures how far a voltage can travel along the membrane before fading. So let's make our little, it's a poor axon, but that's an axon. And we're going to bring in our sodium channel. When action potentials happen, the sodium rushes in. And we start to have a change in voltage. So the length constant measures how much that voltage is going to travel down the axon. This is the Blong from class, where myelin comes in and improves these properties. It reduces capacitance, and it increases the length constant. So action potentials can move much farther through the membrane. So if we have a myelin, this will cause it so that there's less, the membrane is stronger, basically, and so that it can travel more and it's less permeable. Okay, well, in summary, the resting membrane potential is created by selectively permeable membranes and ion pumps, while the action potential relies on voltage gated ion channels, cycling through different phases. Graded potentials are local and variable, while action are all or nothing signals. Um, and then finally, capacitance is the length constant determine the signal speed, and myelin dramatically speeds up the speed of the voltage. Thanks for listening.